Okay. Hi. I wasn't really sure what I should talk about when I'm here. Is more physics or more code? Or yeah. So I will start about what I've done or what I do normally, and try to say what do I need in the code definitely. So I try to make simulations of the corona, and my main subject is the heating of the corona. Perhaps everyone knows that the discussion about it is magnetic heating or is it acoustic waves dissipating so that the corona is heated. We assume that flux gradient is one of the main part which heats the corona, and so we have one dissipation in the atmosphere. The other question I was concerned about during my PhD is why is this corona so structured? So we have these energies released in the atmosphere, and the heat is only conducted along the magnetic field lines. So you get these nice loops which you can see on X-ray images from the sun. The heat conduction is described by the Spitzer heat conduction formula, which is the relation proportional to temperature up to the first half. And there you add 2 times the unit vector of the magnetic field, and you get the anisotropic heat form, heat conduction form. The problem now is for the simulation is if you start from the solar corona, from the solar photosphere, which is about 3,000 Kelvin hot, up to the corona, which is 1 million degree. I have a really high gradient in temperature in the transition region. And the question is, can we really model this with pencil code, because other codes already did, and if the code is suitable for us, and if it's fast enough, and if so, can we do more than just a simple simulation? So, to do the simulation, I have to verify first is this work or find what is in the code. So I test first the Spitzer conductivity. Easiest way to start is 2D and ideal MHD. So I have beta nearly equal to 0. And then the Gaussian blob of entropy somewhere in the middle. You see the magnetic field lines. So what comes out is that the energy is only distributed along these field lines. Here you see the same for the temperature. The only problem is when you use this Spitzer conductivity that the outer parts here are not exactly 0 as they should be. But for the initial condition, we had here a Gaussian blob with almost 0 values here, or 0 values. And if you then run this simulation, you get a slight increase, but it's less than a promille in comparison to the main value of the temperature. So this is just a numerical effect, which is, I guess, okay for the simulation. And next step is, okay, let's think about some physics which goes on. And last time I was here, I had the idea about doing something with magnetothermal instability. And this instability only works if you have these anisotropic heat transport. This stability is similar to the magnetorotational instability. So if you write down the formulas, it looks very similar. This stability only works in a stratified atmosphere where you have, which is convective stable. So that you have an increasing entropy gradient, a positive entropy gradient, and a negative temperature gradient. So red means warm and blue means cold. If we now have a part of the atmosphere which is rising up, this will expand algebraically, and there will be no buoyant force, so it will fall down back and nothing will happen, it just will oscillate, so nothing serious will happen. If you now add a magnetic field and you have anisotropic heat transport, the rising part of the atmosphere will now be fed by energy from the hotter lower part, so that this part will be heat up and can rise more, and the more it rises, the more the gradient of the magnetic field lines changes, and the more heat can flow into the to this part, and it will rise exponentially, and so we have the instability going on. To do this, just the small formula. We start with a polytropic atmosphere. I guess a lot of people have seen these formulas. We have this assumption, equation of state, entropy, and now you get the definition for a stable atmosphere without these anisotropic heat conduction. The RDL-MHD is also clear. It's just for myself these formulas. So we have this conduction equation, equation of motion, entropy equation, and here you have the Spitzer conductivity with the unit vectors of the magnetic field. Now you need to analyze this. You need to add a perturbation and linearize the equations, which I did here. So you get a set of equations.
And excuse me, can you show your general equation on this slide before?
So you have the equation of state, entropy equation, or the definition of entropy concerning temperature, density, and pressure.
Yeah, but, okay, you just assume that you have hydrostatic equilibrium, but what's about radiative equilibrium?
There's no radiation.
Because in the polytropic atmosphere, the radiative equilibrium implies that the radiative conductivity is constant. In this case, you just apply the hydrostatic equilibrium, so your atmosphere is not in a radiative equilibrium at the beginning, right?
Right, yeah.
Do
you mean?
So I think you can get around this. I understand what I mean. So you have, first of all, you have to set up your thermostat, of course you're saying. And for that to have, you need a finite conductivity.
Yeah.
And first of all, it would normally be constant. It would probably also be small. Okay, now, in addition to everything, you have an additional component to the conductivity, which is only present if there is magnetic field, and then it's aligned with magnetic field.
Yes.
And it's this additional thing, and it must be sufficiently big. By the way, you have, of course, actually two conductivities. Can you show your
it's
exactly that one. There's a chi and a chi prime.
Or chi 1, chi 2.
Exactly. So you actually have this. So you're talking about the K2, and that's like this in the equation. And K2 is a constant.
These are constants. This is isotropic heat.
And by the way, maybe it should be T.
Yeah, it should be T.
Not S.
That's T.
Yes, right. All right, good. So it's okay.
Okay, you linearize the equations. You get these omega as frequency, and you get this set. You can try to solve it and get the dispersion relation, which looks like this. And I added the atom speed, which you can get out of the B values, and it's quite difficult to analyze this one, but I only need a very weak field for these anisotropic heat conductors. Just the direction of the magnetic field is important. So I can neglect the values of the hand speed, which I did here. So the dispersion relation looks much shorter and easier to understand. So I get a value for omega. My omega is very small. I can also try to solve this dispersion relation for this G, which is correlated to the K1, K2 value of the heat conduction terms in dependence of the frequency. And then you can plot the dispersion relation, which has a real part or a positive part and a negative part. The negative part includes two different parts, which is just shown here. It's blue and red, and green is positive. What we can try to make in this code is only the positive part, which is clear. And that I did. And here you see a sample run, hopefully you can see it from the back. Here you see the dispersion relation using the initial conditions in the start-in file. It's a line, and here you see a measured or several, 1, 2, 3, 4, 5, several runs with different k values. Here's a typical run. You have here the time, here the RMS value of the velocity. Here you have the linear rise of the RMS value which is going on. This shows that in principle that we can reproduce these magnetothermal instability. So I assume that these Spitzer conductivity works in the code if we can reproduce these dispersion relation like it's shown here. So we can I could do a more physics about this, that you have the turbulence going on here, that during this rise of the velocity also the RMS value of magnetic field increase, or we have increase of magnetic energy and stuff like this, but it's not the point I will talk about here. I will continue with my main topic, which I know is now that the peak conduction works on the topic, and I will do the corona simulation, which is a 3D simulation. So we run a simulation with 256 cubed grid points. We have the full 3D MHD equations, except of the corrosive force, which is neglectable for us, or at the sparse atmosphere. And we do it in non-equidistant grid. So I guess I'm the only one here in the room which is using non-equidistant grid in pencil code. But I think it works fine and everything is included. So for simulation, we have a magnetogram from the MDI at the lower layer of the cube, which looks more like this one. And we have a positive and negative fluxes coming out. This will build a loop like this, and you have here around artificial produced boundary condition which shows a granular pattern of the solar photosphere. This is the food point motion which was first calculated by an external Fortran program and then just added as boundary condition on the lower boundary. So after a while this will produce a temperature profile which looks more like this. Now we have here the bottom layer. This is vertical z equal to 0 up to 256 grid points. We have temperature profile which looks like this. There's a photosphere at 3000 Kelvin up to 1 million degree corona. Here we have you see the mean value along this height and the max and the minimum value along the side. So you have to think about this always is like a one layer. So what you see, we have no spread. The mean, maximum, and the mean, maximum, minimum value are all the same, because I'm here using one of these boundary conditions, which is called Newton cooling, what we had discussed this morning, which was written here somewhere. Perhaps you remember, and this works quite fine. I have set the, and I was talking about boundary conditions with all the other people today also. Other boundary conditions on the lower layer are that I have frozen magnetic flux. That means that the ECHA value is 0 for the vertical component of the magnetic, in the vertical component of the reduction equation. Velocity is set to 0 and other stuff is not important. The temperatures set by Newton cooling mostly. And in the upper layer is still a big problem. As you can see here already, there's a peak which is definitely not what I want to see. It's due to the improper boundary condition. Since I'm using non-equidistant grid, I have lots of grid points around here, and only just 1, 2, 3, 4 on the upper part. Then at the end, I will hope just to cut off the upper part of my atmosphere and say this has nothing to do with physics, and just analyze the rest of the data which is below this one. So that's the way I just to go around the problem with the boundary conditions.
So what boundary conditions do you use?
Just think about anything and it's okay.
But you could probably use the sequential.
This would, yeah, that's learned here, unfortunately, so it would be one chance. Other way would be just to add another Newton cooling for temperature on top and another Newton cooling for the density.
No, but what do you use for this? I mean, can you
Yeah, here I switched from time step before to time step what you see here. I just switched from A2 unsymmetric respect to the boundary value to a symmetric or to constant temperature to CT, C capital T. So I have only one temperature value here. That's why I have T like this. The other big problem is that the magnetic field on top of this atmosphere. And the picture.
Just I have a question.
Yeah.
At z equals 0, is that the top of the constant?
This is the bottom of the no, here is the photosphere.
No, it's a complete atmosphere, so not just the corona because
no, it's the complete atmosphere. You have here the photosphere on the lowest grid point. Then you have the temperature minimum, so that means the photosphere is
the minimum. Okay.
Then you have the chromosphere around here.
Okay. And
the transition region, which is spread to the same.
Okay. Are you saying are you speaking about the straight line, the line in the middle?
Yeah, the line in the middle is the mean one. As you have seen, but
okay.
This is just a 2D cut through a box.
Are you meaning that in the corona after is adiabatic? Because you have a quite constant temperature, even if...
In mean value, yes. This is a mean value of 256 squared points. So this is a mean value of all the points which are along this surface. So
no, but it means that you have a constant temperature like this.
yes.
And there's heating, right? From the resistive heating.
Yeah, there's heating. We are showing next slide. And yeah, so I get the heating if I have magnetic flux which is pushed around on the bottom and will break on top, and then ohmic heat will dissipate. That's how I get the energy up to the corona. The problem is that even if I start with the potential field extrapolation of the magnetogram, I will be way apart from the potential field configuration. So I definitely have no potential field in the corona, and I don't have something which is force-free magnetic field or something else like this. This is really a highly structured, non-trivial magnetic field configuration. And on this magnetic field configuration, it's really hard to decide what boundary condition what to use. So there are several options in the code. There have been 3 different potential field extrapolation, and yeah, I can't use any of those because I don't have any easy magnetic field configuration below this top boundary. So I just decided to take something like A2 or antisymmetric with respect to the boundary value, and I quenched with a easy function the ohmic heat away on top or below this boundary condition, boundary value.
I mean, probably not to 0, but to some average value.
To 0.
To 0?
To 0.
So then it cools.
Sorry?
Would it then not cool?
Yeah, but yeah, it would cool, right? So I have radiative cooling in this atmosphere too. It would, if I don't heat anything, it will cool down. But anyway, I have to keep the temperature at a certain value by some Newton cooling or some other boundary conditions.
Heating, you mean, yes, right.
Or some artificial heating. So I don't.
Okay, then it's
all the 3 points below these boundary conditions I neglect during my data analysis because they are really not physical. Like, there's no chance for me to find some boundary condition which I can use later on to understand. That I really have the heating in this atmosphere compensiert. is if I try to analyze it, so I try to calculate the emissivity for a certain line. So if you assume atomic transition, and if you assume atomic transition, so we have one wavelength so which emits the light, so and I took the neon 8 line, which should represent the lower corona, and I calculate this emissivity in a very simple way. And what you now see is here that this is a example through the box. So you see several layers added to one slide, and you really see loop-like structures. So you can see from the back, you see loop-like structures. So that means you have hot loops and cool surroundings and cool inner part of the loop. You have a big loop, a small loop, and stuff like this. This is a look through from the X direction. Then you can have a look through the box from the Y direction. You also see here a loop. Here's a loop which is aligned of the line of sight. Here is much better. And if you look from top, you see more or less the magnetic field configuration with the loops, which seems to be like this. And you see it's really not trivial and hard to understand on the boundary. Then I just want to say something about one can switch between entropy and temperature as pencil values. So pencil values like density and velocity and vector potential. And in the beginning I started with entropy, which was the biggest file and the most routines were included there. And when you try to write this Spitzer heat conduction in the entropy form, when you start with this form, this is the anisotropic tensor, which includes the isotropic part and the anisotropic part. We have to reform it down to the pencil values, more or less. Then you can get these gradients of the conduction factors, and you get the E and E terms here, and E represents the temperature here. So normally Spitzer would be temperature. The temperature is proportional to gradient of the divergence of gradient of temperature. Now you have to add in the code, instead of E, entropy plus something with density, and for the magnetic field add something with the curve of vector potential. And here you have the first derivative of the E value, which would be the second derivative of A. So this easy looking formula is now split into lots of different parts of calculations with lots of differences. And it is, if you have so many parts you have to add, it's easy to make an error, or an error which will increase. So perhaps these are too many terms. So, and I think my code was not stable enough due to this problem that I had too many parts here, because the temperature gradient is really huge in the transition region. If I now switch from the entropy part to the temperature file, I get few less terms here if I just have one instead of two here with here. So, and the calculation you see here was done with the temperature instead of the entropy as pencil value.
I actually think this is a proper instability. I mean, I found the same thing in connection with cosmic rays. That, or maybe it was with this. At least the entropy formulation was not working. It produced instability, which sounds exactly the same as what you're saying. for field line diffusion.
Produce instability. Yeah.
Because you have because the diffusion operator is then composed of an entropy second derivative and a density second derivative.
Yeah.
And it's feedbacking only on the entropy, not on the derivative, on the log rho, of course.
When you say proper instability, you don't mean physical instability,
It's
obviously,
mean
because
no, but
the
it's
description should be equivalent.
a proper numerical instability.
What do you mean? So it means that it blows up, or you
Yeah.
just
It produces ringing, actually very resolved ringing, perpendicular to the lines. Did you see that?
No, I saw just Persian code.
So maybe you didn't look at the images.
No, I couldn't find anything. Mostly, what I found mostly was that really at the transition region, this that I really got the peak here, and this was in rising high. That's all that I see. And this is perpendicular to magnetic field. So mostly at this point, I got. I guess the problems here you get when you have really extreme parallel, so the gradient of the temperature is parallel to the magnetic field. Then you get a small value which could increase but should not be there. And you get problems if the gradient of the temperature is very high and is perpendicular to the magnetic field. Then you get also problems in this formulation. Like, didn't saw any rigorous objects or something.
I mean, the basic conclusion to take from this is, of course, to say that there's nothing really too magical about using entropy. I mean, we can equally use temperature. Sometimes when entropy is better, and it's often really more messy, and temperature is much easier to use.
At least from the right moment.
But hopefully certainly temperature was not much easier. Which temperature module are you using, by the way? And that's for ideal, right?
Yeah.
And I'm not too sure how. I mean, they are all not completely fully compatible. I mean, they are compatible in many respects, but there could be additional possibilities in other modules which are not existing in the other ones, obviously. That's the only downside. So we cannot just exchange them without too much, without any thinking. Yeah.
So again, yeah, I would say now for me it's since I switched to temperature, it's almost all fine. What will I do in the future with the code? So I'm quite happy with the code. I think it works fine. I really want to add a real convective layer of the granulation, which I now add by forcing the boundary to be like granulation. Like to have a real convective layer, like the sample one which he added to the sample code, where you have a granulation and you have transfer in the sample. So I'm wondering if it's possible to have this convection and the transfer and the corona and in a usable Cebu time. So can I do this simulation? I will figure out this soon. And I will add the time series magnetogram. So right now I just start with magnetogram observation, and this will be shuffled around, but I can't compare with observations which has the time series of magnetograms. And to film my series, I have now to try different setups, white sun, white diffraction, and I have to understand and analyze the data and compare it with observations.
Okay, thank you. Questions?
And if you want to use radiative transfer, then there will be. You will have to. It's difficult to get this working with an unstructured grid. I think.
You mean
Non-equidistant.
A non-equidistant. So you would probably not be able to use any other ray directions but the vertical one.
Yeah, but that's because of interpolation. And you think it's very serious, the issue?
well, it would certainly require some serious coding, I think, to get this working and non-equidistant, and not even sure that I should probably better. I think it's difficult. It would be major